1940 hours, test log 14, I pulled the pistol grip cocking release, the engagement slipped. The bolt ran forward. On its own, inspection notes show a round chambered without clearance. The report was sealed that night. In June 1940, the United Kingdom was reorganising for a defensive phase of the war. The main front line was no longer only overseas, the war was reaching British industry by air attack. Government planning treated factories as targets and treated machine tools as a limiting resource. The Army's small arms system was forced to think in terms of single points of failure. Within an infantry section, the Bren-like machine gun provided the sustained automatic fire that shaped movement and control. It was accurate and stable on the bipod. It was also a manufactured object that demanded machining time, skilled fitting, and a protected production line. In 1940, manufacture and key tooling were concentrated. Concentration simplified supervision. It also created vulnerability if a plant was damaged or if transport links failed. The tactical problem was straightforward. A section without a functioning light machine gun loses its base of fire. Rifle fire cannot compensate for the same sustained effect under suppression. The strategic problem was less visible but decisive. If production of the Bren stopped, there was no fast substitute that could be issued with existing magazines and ammunition. The Soviet Union faced a related class of pressure. Infantry automatic weapons were consumed by expansion and losses. The institutional solution was not to wait for perfect manufacturing conditions. It was to accept simplified production methods where function could be maintained, and to reduce dependence on high-precision machining when factories were relocating or being overtasked. Britain's 1940 emergency programme sat in the same category, but inside a different industrial base and inspection culture. A requirement for an emergency light machine gun was recorded by British small arms authorities in mid-1940. The intent was insurance. The new weapon had to preserve section firepower if the Bren supply chain was interrupted. It had to be capable of manufacture across a wider range of workshops than the Bren. It also had to avoid creating new logistic pipelines. That meant the standard .303 British cartridge, it meant use of existing Bren magazines, and it meant a layout familiar enough that training could be adapted with limited delay. The procurement logic forced a compromise. A gun designed for dispersed workshops still required someone to create the design, produce drawings, and define inspection gauges. A prototype program was therefore placed with an established firm. Birmingham Small Arms in Birmingham received a War Office contract for prototypes. The lead designer was Henry Harry Faulkner. His task was to produce a workable Bren-type light machine gun, then strip the manufacturing requirements down until the gun could be built in a broader set of facilities. The project became known as the Beazle. Later documentation also uses the name Faulkner for the same program. The naming is an administrative detail, but it reflects the weapon's status. It was a contingency design. Yet it did not develop a stable service identity through issue and long use. Development timing shows the underlying constraint. A requirement written in 1940 did not yield an immediately manufacturable replacement in 1940. Tooling for pressings must be made, welding jigs must be built, gauges must be designed and distributed, drawings must be standardized. Each change requires another cycle of build and test. By the time the design was mature enough to be considered for production, Britain had already diversified Bren manufacture and reduced its single-site exposure. The emergency gun became less urgent without ever becoming irrelevant on technical grounds. The Beazle was intentionally ordinary in appearance. It remained a light machine gun with a top magazine, a pistol grip and a bipod. And it kept the same general silhouette because the constraints were practical. The Bren magazine already existed in quantity. The .303 cartridge is rimmed, and reliable feeding depends on careful control of rim stacking. The Bren magazine geometry and follower arrangement already addressed that. Reusing that system reduced risk and reduced time. The main design change was the method of making the receiver and related components. The Beazle used sheet metal pressings welded together to form the main structure. Welding and pressing convert machining time into jig time. The factory effort becomes one of consistent forming, consistent welds, and consistent inspection, rather than fine milling. That is compatible with the larger set of firms provided the inspection system can travel and enforce standards. And internal parts were also adapted to reduce machining. The bulk carrier group remained conceptually similar to the Brens, but it was reshaped to minimize machining operations. The geometry became more block-like. Engagement surfaces were kept functional rather than elegant. This choice reduces skilled labor input. it increases dependence on correct heat treatment and on consistent tolerances, because simplified shapes can hide small misalignments until wear reveals them. The firing cycle followed the standard pattern for a gas-operated automatic light machine gun. The working parts are held to the rear on the sear. Trigger release permits the bolt group to run forward under spring pressure, strip a cartridge from the magazine, chamber it, lock and fire. The gas is tapped from the barrel and drives a piston that cycles the working parts to the rear, extracting and ejecting the spent case and returning to the rear position for the next shot. The gun was designed for automatic fire, with the gunner controlling bursts rather than selecting single shots. Several controls were changed to remove parts and external fittings. The Bren-style in its simplified form did not use a conventional external cocking handle. Instead, the pistol grip itself acted as the cocking device. A release had to be operated. The grip slid forward to engage the working parts, then pulled rearward against spring force to cock the action. This saves a handle, its slot, and its associated fitting work. It introduces a different maintenance burden, and a sliding mechanism must remain free of deformation and heavy fouling if it is to remain usable with gloved hands and limited lubrication. Another simplification removed the Bren's adjustable gas regulator. A fixed gas setting reduces machining and reduces parts count. It also reduces the user's ability to compensate for fouling or ammunition variation. A fixed system must be balanced so it will cycle reliably when dirty without overdriving the mechanism when clean. The burden moves to the designer and to the test program. The accepted margin is set on a range and then enforced by inspection. Barrel handling was also simplified, but kept within familiar doctrine. The intent included reuse of Bren barrels from stores to accelerate production if the emergency trigger was pulled. Prototype examples show proprietary barrels as well, with integrated features such as a tubular flash suppressor and a simple sight and gas block arrangement. Barrel removal was achieved through a lever system that required the mechanism to be in a controlled state before the barrel could be released. That aligns with the institutional goal of preventing uncontrolled bolt movement during handling and of forcing a repeatable sequence for armourer training. Dimensions and weights recorded for surviving examples place the Bren-style in the Bren class rather than below it. Overall length sits around 1.2 meters. Barrel length varies by variant and by how measurement includes muzzle fittings, but it sits around the 0.6 to 0.65 meter range in museum records. Caliber remains .303. Weight figures reported for prototype configurations cluster around roughly 10 to 11 kilograms, depending on fitted parts and measurement method. The design did not become a lightweight weapon. Its purpose was production resilience, not reduction of carried mass. The performance envelope followed the cartridge. A .303 light machine gun delivers rifle-class ballistics. Effective range in doctrine is governed by sights, stability, and dispersion, rather than by the cartridge alone. A gun that reuses Bren magazines and fires the same ammunition also inherits the same ammunition hazards. Rimmed cartridges demand correct magazine loading. Damaged magazine feed lips produce misfeeds. Weak magazine springs reduce reliability. Those faults are managed through inspection and replacement rather than through narrative. The Bren-style's failure points were the predictable ones for a pressing and weld receiver combined with a high-rate moving mass. Weld seams carry repeated stress. If a weld toe cracks, stiffness drops and alignment changes. Alignment changes increase friction in the bolt's travel. Increased friction reduces cycling margin and increases stoppages. Heat-affected zones from welding can also change local material properties. The mitigation is consistent weld procedure and consistent inspection, both of which become harder as production disperses. Pinned and welded assemblies also add long-term wear issues. A receiver that is not a single block can loosen at joints under repeated recoil impulses. Looseness changes the relationship between bolt face, feedway, and chamber. On a rimmed cartridge, that relationship is sensitive. If the bolt face rides incorrectly over a rim, it can produce a bolt-over-base stoppage. If the magazine sits too low, stripping fails. But if it sits too high, the bolt can strike feed lips and slow. These are gauge problems that expand into training problems if variation is not controlled. The sliding pistol grip cocking system adds its own hazards. The release lever and its engagement surfaces must remain intact. If the system allows partial engagement, the working parts can slip under spring force. Unintended forward movement can chamber around without a deliberate firing sequence. In safety terms, that is treated as unacceptable. The sear engagement and the robustness of the cocking interface become safety-critical parts, not merely convenience parts. A fixed gas system produces another observed category of failure. If the gas setting is marginal, a dirty gun short cycles. Short cycling produces failures to eject and failures to feed. If the setting is aggressive, the mechanism cycles violently. Violent cycling increases wear on locking surfaces, increases peening, and can initiate cracks in welded receiver structures. The trial program's purpose is to determine whether the chosen setting produces acceptable stoppage rates across expected conditions without consuming receiver life too quickly. Disassembly and maintenance features were designed to reduce dependence on special tools. Prototype descriptions include a release under the barrel that allows removal of working parts to the rear once the butt stock assembly is detached, and a dust cover arrangement that can lock when no magazine is fitted. These are maintenance decisions. They are also logistics decisions. A weapon intended for dispersed production must also be serviceable by dispersed armourers, and often under rapid training and with limited spare tool inventories. The bipod choice illustrates another trade. A heavy, strongly locking bipod adds weight and machining effort. It also stabilizes the gun. Stability reduces dispersion and reduces the tendency of the muzzle to strike the ground during bursts. In institutional terms, that reduces accidental damage to the barrel and gas system. In a contingency design, weight is accepted if it reduces field failures that would otherwise overload the repair pipeline. The Ibicel did not have a conventional combat record. It did not enter serial production. Its operational use exists as trial use and as planned issue. The first deployment of the B-cell was therefore on British test ranges under Ordnance and Inspectorate supervision, not with operational battalions in combat. As the unit involved was the evaluation system itself. Prototype teams, inspectors, and representative soldiers assigned to fire and handle the gun under controlled conditions. The mission context was procurement insurance. The purpose was to determine whether Britain could preserve section firepower if bombing or disruption removed Bren output. Trial use would have involved proof endurance firing and inspection. It would have included firing schedules designed to observe heat effects, stoppage patterns, and receiver fatigue. It would have included tests of magazine interchangeability and of compatibility with standard ammunition types used in service. The outcomes were recorded in the normal language of the system: stoppages per 1,000 rounds, parts wear, receiver cracking, and recommended modifications. Though the absence of a large field record does not remove the existence of that paperwork. It concentrates the story inside the evaluation archive. Planned issue, had it been triggered, would have been conservative. The gun would have been issued into the same infantry role as the Bren. Carrying method would follow existing practice. Magazines would be carried in standard pouches. Ammunition would remain in standard packaging. Training would adapt Bren drills with changes for the cocking method and the absence of semi-automatic fire. Safety procedure would emphasize bolt position, magazine removal before handling, controlled barrel change, and inspection of cocking and sear interfaces. Distribution planning for a dispersed production gun is itself a form of operational planning. Receivers and trigger units could be built in one set of firms, barrels and gas parts in another, bipods in another, and final assembly in a fourth. Every transfer requires inspection and documentation. Every inspector must carry gauges that define acceptability. The advantage is resilience against a single factory failure. The cost is a larger paperwork footprint and a larger travelling inspection structure. Strategic impact came from that insurance value. The programme signalled that Britain could build a Bren-class light machine gun, using pressings and welds if forced to do so. It also demonstrated that even an emergency gun is not instantaneous. Design and testing absorb months, tooling and gauges absorb further time. The insurance works only if the programme is started before the crisis becomes total and if its drawings and gauges are held ready for distribution. The Soviet comparison clarifies why such insurance mattered. Under pressure, Soviet industry relocated and accepted simplified manufacturing in many weapon categories. That approach produced variation and wear issues, then absorbed them through volume and through a rugged inspection and repair system. Britain's Best-style attempted to widen the manufacturing base in a similar way, but without the same scale of relocation and without converting the entire system to the contingency product. It remained a prepared alternative rather than a forced substitution. Institutional psychology was recorded in administrative terms. The gun was labelled an emergency substitute. That label affects acceptability and confidence. Acceptability affects maintenance compliance. Compliance affects stoppage rates. The stoppage rates feed back into procurement decisions. For a gun built in dispersed shops, variation between examples would also have been a concern. Variation increases unusual malfunctions. Unusual malfunctions increase distrust and create demands for replacement. Such patterns are treated as system variables, not as emotional commentary. Enemy reaction was structurally limited. A weapon that does not enter service does not generate battlefield intelligence and does not justify a specific countermeasure. German small unit tactics already treated light machine guns as priority targets. No additional adaptation would have been required to address a unissued British prototype. The program declined because its trigger condition declined. So the immediate fear that Bren capacity could be erased by bombing diminished as Bren production diversified and the industrial system adapted. The replacement was therefore the continuing Bren, not a new standard. The Bicelle remained as a demonstrated option that did not need activation. It was cancelled by redundancy rather than by failure. In post-war terms, the Bicelle's legacy is administrative and technical rather than tactical. It shows a wartime procurement system trying to remove a single-point risk in infantry firepower. It shows an attempt to convert a refined machine gun into a version shaped by pressings, welds, simplified controls, and reduced dependence on skilled machining. It also shows the boundary of simplification. The gun remained heavy. It still required careful safety control around sear engagement, cocking interfaces, and receiver fatigue. It was ordinary in appearance, but it represented a calculated response to industrial vulnerability. This weapon was a technical decision born from wartime pressure, effective on paper, limited in the field.